Good afternoon, everybody. So today we will going to learn one paper which is nomenclated as Operation Research. In this paper, one topic we will learn today, which is called basically LPP, Linear Programming Problem. So basically, from the nomenclature it is clear that we are dealing with the linear equations, but in the operation research we are not dealing with the equations. Basically we are dealing with the inequations. What is inequations and what is linear equations? Already you know that the linear equation in one variable can be represented by ax plus b equals to 0. Or you can say ax plus by is equals to some c. Another, you can consider a linear equation in two variables, ax plus by plus c is equals to 0. So these are the linear equations in one variable, in two variables, and so on. If you want, you can extend that one. So whatever we will learn today, all are linear equation or inequation. So what is inequation? You know about the inequality. So basically, just a minute, I would like to erase these portions. In the term of inequality, if you got ax is less than or equals to b, instead of equality, if it is either less than type or greater than type, then we are saying that these are the inequality. But one thing we will mention here, when you are considering the equation ax equals to b, you can have here that x is equals to b by a is the unique solution here. But it does not represent the unique solution. You can see here, from here you can write down that x is less than equals to, you will get here b by a. Means it represents a set of points. So in the LPP, you are not getting only one solution, you will get a set of solution for any inequality. So a set of points you will get from here. That when we will go for, then we will discuss these things here. Now, let us go for the basic part, that what an LPP contains. So already I mentioned that in the LPP you will see that not the all equations are present here. Maybe some equations consist with some inequality term. So in the LPP there is three basic part which is very important one. Number one, objective function. Second one, objective functions basically is nothing but some information will be given to you, and from there, okay, depending on the information, you have to find out that what is the objective of the problem. And in the most cases, we have seen that the objective function will be either maximization or minimization. Okay? And the next thing is nothing but the constraints. Means with which respect we will optimize Optimize means either maximize or minimize the objective function. And at last, you must remember, this is a very important one, which is called the non-negativity restriction. So these three parts must be present there in any LPP. Okay. Now I am going for the next slide, where we will try to represent that what is the form of an LPP. So let us consider a problem here. Then I think it will be more clear to everyone that what it represents basically. So let us choose a problem. Maximize z is equals to 4x1 plus 3x2 subject to 2x1 plus 3x2 less than equals to 4. 4x1 plus 7x2 greater than equals to 9, and 3x1 plus 5x2 equals to 10. So x1, x2 greater than equals to 0. So here you can see that this is your objective function. If I go for the different color, you can see here that this is our objective function. So this is number 1. These three portions is the part belongs to the 2, and this is the organism. So these three parts will be there in any LPP, and obviously we will learn today that how we will solve this. Okay, because from any given information you can find out what is the LPP. For that obviously we can go for one example. Okay, but before that I am showing you that what are the different types of function it may carry. Here you can see this is the less than type constraint. Here you can see this is the greater than type constraint, this is equal type constraint. Okay. So in this case, what type of region or what type of solution we get in each every cases where we go for the solution, at that time we will discuss that one. Okay. So let us go for one example where we want to find out the LPP. What will be the linear programming problem? So let us consider one official project, or you can say IOC has total number of shifts, maybe you can consider as 6 shifts are there. So I am writing down the shift and the minimum number of worker minutes. So first shift, if you consider as 12 a.m. to 4 a.m. Next, 4 a.m. to 8 a.m. Then 8 a.m. to 12 p.m. 12 p.m. to 4 p.m. 4 p.m. to 8 p.m. and 8 p.m. to 12 a.m. So these are the different shifts. And here, what is the minimum number of workers needed? This is defined. Let and there 7 workers needed. From 4 to 8, let it is 9 minimum worker needed. From 8 to 12, let it is 12 worker needed. 12 to 4, you needed here 22 workers. 4 to this, let it is needed 11 workers, and let this is 4, you needed 9 workers. So this is what information is giving to you, and also it is giving that any worker will work for 8 consecutive hours. 8 consecutive hours they will do the work. And we have to find out what is the LPP. So this is the simple information is giving, and we have to find out the LPP from there. So how we find out this? So this is very important problem, because in the most corporate sector they will follow these type of situations, and obviously as you know that you have to assign the workers. So as a teacher always wants to minimize the total number of workers. So the objective of this problem is nothing but we have to minimize the total number of workers, and for that we have to formulate first, and then we will go for the solution. So the question arises, how we do this? So obviously for that, basically we followed these techniques. Let us assume that x1 number of workers enter into this sheet. x2 number of workers enter into the second sheet. x3 number of workers enter into the third sheet. x4 number of workers enter into the fourth sheet. x5 number of workers enter into the fifth one, and x6 number of workers enter into the last sheet. So these are the number of persons. So at 12 a.m. x1 number of workers comes to enter into the system. At 4 a.m. x2 number of customers enter to do the work. Now the question arises, so how will we formulate this? So in the whole day, 24-hour system, you can see that the total number of workers enter is nothing but x1 plus x2 plus x3 plus x4 plus x5 plus x6. It is obvious. So as an teacher, what you will want? We want what? That this is our total number of workers, and our aim is what? We have to minimize this. So this one is nothing but our objective function. Now, with respect we will minimize this. So for that we have to find out what are the constraints. Okay, so you can see very interesting thing here. And it is given that any worker will do the work for 8 consecutive hours. So the person who is entered in the first session, he will not go out after the first session. He has to work for the second session also. Who entered the second session, he has to do the work in the third session also. So on that way, if you see that in the second session, the total number of workers will be what? In the second session, total number of workers will be, you can see here, so you will see the total number of workers in the second session will be x1, who has done the work in the first session. the person who are coming in the second session. Just a minute. So, this is the total number of persons in the second session, and the minimum number of worker required is what? 9. So, obviously this must be greater than equals to 9. So, I think it will be better if we go for the next slide, and there we will write down the expression. So, you can see, so we are writing here, minimize z is equals to x1 plus x2 plus x3 plus x4 plus x5 plus x6, and subject to the constant, first one what you got, x1 plus x2 greater than or equals to, what you got from here, you can see here, this is written as 9. So you can get from here, this is equal, greater than equals to 9. What about the second constant? You can see from here, if you go here, in the second constant, in the second half, x2 number of person enter, and x2 number of persons continuing, and x3 number enter on that session. So total number present in this session is nothing but x2 plus x3, which must be greater than equals to 12. So we can say from here that the second constant will be x2 plus x3 must be greater than equals to 12. Similarly, x3 plus x4 greater than equals to x4 plus x5 greater than equals to x5 plus x6 greater than equal to, and obviously who are doing entering into the last session, they will do the work with the first session person. So that's why these terms we are collectively getting from here. These will be what? 22, 11, 9 and 7. So we are getting here 22, 11, 9 and 7. So these are the constraints with respect to we have to minimize this. This is our objective function, and obviously at last x1, x2, x3 up to x6 must be greater than equals to 0. So this is the one way to find out one LPP, where you can see that several number of variables is present here. So I am just directly going for one example by which we will try to find out that how we will solve this. So obviously when you will go for the solution, you will learn two techniques. Number one, so basically solution of LPP can be done by two techniques. Number one is graphical method, and second one is simplex method. So the easier one, but it has some drawback. We are going for first, and today we will learn the graphical method. But in the graphical method, you know that there is some drawback. That if the number of variable is greater than 2, you cannot solve by the graphical method. But in most cases for our real life, we have several problems which contains only 2 variables. So, and obviously graphical method and simplex method are related regarding the solutions. So that's why we are going for first the graphical method, and then we will learn the simplex method. But today basically we are emphasizing on the graphical method. So for the graphical method we are choosing, so initially for the graphical method, so we are choosing one problem and then we will discuss. Basically, we will choose 4 different problems because you will see that in any LPP there exists 4 type of solution. Number 1. So, in both cases, whether it is you are doing by graphical method, by simplex method, in all cases the solution, just a minute, solution type, number 1 unique, number 2 many solution, number 3 unbounded solution, and number 4 no solution. It is not necessary that every problem has a solution. So that's why these 4 types of solution we will face when we will go for the solution either by graphical method or by simplex method. In all cases, we will face these 4 different types of solutions. What it implies, and I obviously discuss these things by the example so that it is clear to everyone. Okay, so let us go for one problem first and then we will discuss. So I am going for one problem. Max z is equals to 4x1 plus 3x2 subject to the constraint 2x1 plus x2. 2x1 plus x2 less than equals to 10. Then x1 plus x2 less than equals to 8. And then 0 greater than equals to x1 less than equals to 4. 0 greater than equal to x2 less than equals to 7. So let us choose this problem and try to find out the solution by the graphical method. And first I will ask you that is it an LPP? First question will arise, it is an LPP. Yes, it has objective function, no problem. It has constraint, yes. Any non-negative restriction? So basically, yes, it has a non-negativity restriction in this manner. You can see. If I told you what is the total number of constraints, if you say that 2, then it is wrong. Basically, there exist 4 constraints. What are these? So if you simplify these things, you will get from here, one constant is x1 less than equals to 4, another constant is x2 less than equal to 7, and these two you will write down what? These two you will write down in this way. At last, x1 comma x2 greater than equals to 0. So this is coming from here. So this is constant number 1. This is constant number 2, this is your constant number 3, this is your constant number 4. So these are the constant numbers. And this is your non-negativity restriction. These are for constants. And this is our objective. So, for the graphical method solution, first we will try to find out that how we will draw the graph. So, for that, let us choose this constant. So, to do this, we are going for 2 perpendicular axes. One representing x1, another representing x2. Okay. First we are considering this constant which is written as 2x1 plus x2 less than equals to 10. If you ignore the less than equals to sign, then what do you get? You can write down from here that this is equals to 10. You know that any equation in two variable represents a straight line. So, if you want to find out the equation of line, this is given here. And what will be the equation? You can see here, you can write down x1 by 5 plus x2 by 10. This is equals to 1, which is called the intersected form of a straight line. So, let us, so x1, so the line intersecting x1 at the point, say 5, 0. Just a minute, I need some 5, 0. Another is what? Another is cutting the x2 axis at 0, 10. And we are joining these two lines by a straight line which is represented by now. Actually it was less than equals to. So as I told you earlier that equality sign basically giving the point line over this line. But it was an inequality. So the question arises. What will be the points which satisfy these equations? These inequations, what will be the point satisfying? So for that I have a very interesting thing. Always we will put 0, 0 in this expression. If it satisfies the inequation, then the points lying towards origin. If it is not, then it is away from the origin. So you can see that if you put here 0, 0 in this expression, you will get 0 plus 0 less than equal to 10. Yes, obviously 0 less than equal to 10. So the points basically lie towards origin. Means all the points present here in this direction, all the points are satisfying these inequations. So in that way, the first one we are getting, and we are getting what is the region of the constant first. Second one, if you consider, you will see from the second constant what you will get. You will get here at that time. From the second constant, you will get x1 plus x2 is equals to 8, means x1 by 8 plus x2 by 8 is equals to 1, means it cutting the point here. Eight, 0 and it's cutting the point here which is 0, 8. So if we join these by the straight line in this manner, just a minute. 0, 8, and we are joining these by the straight line in this way. So this is the point, let us assume that. And obviously 0, 0 satisfying this equation. So the points will be towards origin. So in this case also the region is what? Well, towards origin. So from here now you can say that what is the common point who is satisfying both these two equations? So for that we can see that these are the common points which satisfy both the equations. You can say that, sir, why we are not getting these portions? You can see here x1 comma x2 greater than equals to 0. Means we want the points x1 and x2 which are present in the first quadrant as well as satisfying these equations. And due to that reason, we are not going for these portions, we are just choosing this one. So, I hope it is clear to everyone. So, just a minute, okay. What about the third constant? x1 equals to 4 means a line parallel to, we need a line parallel to so we are going for a line which is parallel to इसमें नहीं होगा just a minute I am going for another color in this person so that we can go for this. So what will be the region? Obviously 0 less than equal to 4. So region will be towards origin. So the common region is squeezed now. Go for the constant number 4. If we go for this, you will get this is the region in this manner. Parallel to x1 axis and the region will be also towards origin. So from here we can see that the ultimate common region is nothing but we are getting here is nothing but what this one. And there is a result that if any LPP has a solution, the solution exists at the extreme point of the convex region. So obviously you must ask me what is called convex region, and obviously extreme point you know about that, but what the convex region, this is also very important. So let us go for first there and then we will come here. Convex region. To define convex region, we have to define first convex combination. You know about the linear combination? Let x1, x2, x3 are three vectors. The linear combination of these is nothing but lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3, where lambda I belongs to the scalar function f. This is called the linear combination of the three vector x1, x2 and x3. But if we impose only one condition, which is defined as summation lambda I is equals to 1, where lambda I greater than equals to 0. Sorry, greater than 0 you can say, not equals to 0. So obviously as summation is equals to 1, you can say that this is less than equals to 1 also. So let us do the equality. So if this happens, then only this linear combination is called convex combination. Now the first thing, what a convex combination represents. This is also very good result you have to learn. So for that we are basically simplifying this, that let us assume there exist only two variables. I am not choosing three. For simplification, we are choosing only the two variables. Let x1 and x2 are two vectors. And then, what will be the linear convex combination of this? So, convex combination of this x is nothing but lambda 1 x1 plus lambda 2 x2. Such that lambda 1 comma lambda 2 less than equal to 0, greater than equal to 0, and lambda 1 plus lambda 2 is equals to 1. So this is the convex combination of the two vector x1 and x2. Now what it represents? Just see one thing. If you put lambda 1 equals to 0, you will get lambda 2 equals to 1. So x will become what? X2. You can simplify this in this manner. So I am going for the next place so that we get some space here. So x equals to, you can write down now lambda into x1 plus 1 minus lambda into x2. Just see here. Lambda 1 plus lambda 2 equals to 1. So lambda 2 equals to 1 minus lambda. So we are just putting here and writing in this way that lambda into x1 plus 1 minus lambda into x2 such that, so here only we needed this condition that such that lambda is less than equals to 1, greater than equals to 0. So this is the simplest form to represent the convex combination, and in this case if you put here lambda is equals to 0, you will get x is equals to x2, means the point here x2. If you put here lambda is equals to 1, you will get x equals to x1, means the point or the vectors present here, which is called x1. Now, as it lies between 0 and 1, so you can choose lambda is equals to 1 by 2, and at that time you will get x is equals to x1 plus x2 by 2. You can see 1 by 2 into x1 plus 1 minus 1 by 2 means once again 1 by 2 into x2. So this. So basically, this is nothing but the middle point of x1 and x2. If you put lambda is equals to 1 by 3, you can say x is equals to x1 plus 2x2 by 3. So the point who is dividing the line segment x1 and x2 in the ratio 2:1. So as you can see that lambda lying between 0 and 1 has a 7 number of points. So basically this convex combination representing the line joining the point x1 and x2. So convex combination always represents a line or a straight line, precisely straight line joining the 2 point x1 and x2. And from there now we can define our convex set. So now we are going for convex set. So a set is called, so this is the definition, a set is called convex set if for any 2 point x1 x2 belong, let us say P is called convex set if for any 2 point x1 x2 belongs to P, the convex combination also the member of P. Graphically, I will show you that how a set, you know that any set can be represented by this type of Venn diagram. Let us choose these four type of sets we have chosen here. Now, this is P1, this is your P2, this is your set P3, this is P4. So you know there is several hostels named in our colleges. So you can consider on that way also, P1, P2, P3, P4. Okay. And let us choose 2 points here. Obviously, whatever the point you will choose, you can see that the line joining these 2 points entirely lying in this set. So P1 is convex set. For this one, for this one, for this one, you can see here. If you choose this set, there exists 2 points whose line joining these 2 points not entirely lying on this. Some points are there. Some points are there which is lies outside the set. So this is not our convex. Similarly, here also you will get prominent picture. You can see that this portion not lying on this set. So this is not a convex set. But here, any point, whatever you can choose, the line joining them always lies within set. So this is a convex set. So that things basically we are getting that now if you go for the graphical solution, you will see what? You will see just a minute. I am going for 8. Just a minute. Okay. These 2 slides are same. These 2 slides are same. Okay, now it is okay. So, okay, no problem. So, that things basically we are getting here, and from this, now we can see in the graphical method that we got the common region in this way. Now, this common region is nothing but the convex region. So, in LPP, there is one result that the solution always exists at the extreme point of the common region. So, basically, we have to find out the coordinate of these points. To find out the coordinate of, already we have found out this coordinate. Now, to find out the coordinate of this point, we have to solve these 2 line equations. To find out the coordinate of this one, we have to go for solving the line this as well as this. So on that way, we have to find out the extreme points of the common region. And if we nomenclate this as O, A, B, C and D, we have to find out the value of Z at O, Z at A, Z at B, Z at C and Z at D. After finding out these values, you can now say that as we have to find out, we can see that maximization problem is there. So among these values, what will be the maximum, that we have to find out at that time. And ultimately, you will get the after solving the result, you will get here in this problem. So this is slide. So let us go for this slide now. Just a minute. Okay, this one. So you can see that this is your common region, and in this common region, these are the O, this is your A, this is your B, this is your C, and this is your D. So you have to find out these coordinates by solving the equation of line. To find out these, you have to solve equation. This is your this one equation number 1, and you have to solve here to find out this equation number 4. So just we will see that what is the straight line representing and from which equation you are getting this. So you have to solve this, and after that you will find out JO, JA, JB, and among these results, as the objective function is maximization, you will find out the maximum value, and you will get here after solving this that Z max equals to 26, and which corresponds to the values of x1 equals to 2 and x2 equals to 6. So on that way you can find out the solution of an LPP by the graphical method. But already I mentioned that in the graphical method there is a drawback, and if the number of variables is more than 2, then it is not possible to solve by the graphical method. And obviously for that I already mentioned you that we will learn another technique which is called the simplest method. Though the name is simplest, but it is too much complex to know how the technique is. So that we will discuss on the later classes. But today basically we have learned that how we will formulate an LPP, and then how we will solve an LPP. Obviously, today's class we discuss about the unique solution. The next classes we will go for the many solution, for the unbounded solution, as well as for the no solution. So I hope you enjoyed the classes and go for the lectures. I hope you will able to solve any type of problem. Though it is the first class, so not any type of problem you will solve. But if the LPP has unique solution, this type of problem you can solve by this lecture. Thank you. Thank you.